On October 24, 2025, at 4:10 in the morning, a radio telescope in South Africa caught a signal that should not have been possible. Two precise chemical fingerprints, traces of interstellar water, broadcast from a visitor just 3 degrees from the sun. This was not human-made and not a message, but the first ever radiochemistry from an object beyond our solar system. How did a fleeting blip on a crowded frequency become hard proof of water from another star? And what else might be hidden in that signal? At 3:57 UTC, the MeerKAT control room made a deliberate gamble. A new machine learning filter, trained to spot narrow, comet-like signals in a sea of radio noise, went live just minutes before the scheduled scan of 3I. Atlas. The stakes felt high. Only weeks earlier, a false alarm from the older system had triggered a scramble. Solar interference had masqueraded as a discovery, and the team spent nearly 40 minutes untangling the error before retracting the alert. That episode forced a rewrite of the decision tree, and tonight, every step was under scrutiny. As the clock struck 4:10, the console flashed a spectro anomaly warning. 2 absorption lines, perfectly spaced, each just over a kilometer per second wide. The algorithm's confidence score ticked upward as it cross-checked the Doppler shift, minus 5.6 kilometers per second, a match for the predicted motion of 3I Atlas. Automated routines swept the terrestrial interference database, no match. Within seconds, the system flagged the event as low radio frequency interference likelihood and sent the alert to human review. The senior spectroscopist on shift leaned in, eyes on the spectrum. The lines were clean, narrow, and steady. No flicker from passing satellites, no telltale jump from a solar flare. A quick scan of the solar activity logs confirmed quiet conditions. At 4:12, the operator logged a manual override, marking the signal as an astrophysical candidate that meets cometry and geometric criteria. Protocol called for escalation. The operations coordinator paged 2 independent analysis teams, each tasked with pulling cross-polarization data and reprocessing the spectrum from raw visibility data. The room ran on adrenaline and habit. Every minute counted. The team knew that a misstep, another false positive, could undermine confidence not just in this result, but in the entire Interstellar campaign. By 4:24, consensus was reached. Both teams found the same pair of lines, the same velocity offset, the same narrow width. No sign of instrument drift, no echo in off-target beams. The coordinator authorized a scientific alert to partner arrays, requesting immediate follow-up from Green Bank, FAST, and the Very Large Array, if geometry allowed. The chain of events was logged down to the second. Filter activation, detection, automated vetting, human override, multi-team confirmation, and external alert. The entire triage from first anomaly to partner notification took less than 15 minutes, less than half the time of the September false alarm. Inside the control room, the mood was tense but electric. The new algorithm had done its job, but it was the blend of software precision and rapid human judgment that kept the discovery on track. The team's credibility, built on transparency and speed, would now anchor the story as the world's astronomers turned their attention to a signal that, just hours earlier, had been buried in noise. The spectrum revealed 2 unmistakable notches, OH absorption lines at precisely 1,665 and 1,667 MHz. These were not just statistical blips or artifacts. Each line was narrow, just under 1.3 kilometers per second wide, and both were shifted by minus 5.6 kilometers per second, tracking the exact motion of 3I Atlas as it swept through the inner solar system. For a radio spectroscopist, these details matter. The width tells you how quickly the gas is expanding away from the comet, and the Doppler shift locks the signal to a moving, real-world object, not a glitch or a stray echo from Earth. OH, the hydroxyl radical, is not a random choice. It is the direct product when solar ultraviolet light breaks apart water in a comet's coma. The sun's energy hits water, strips away a hydrogen atom, and leaves OH behind. That is why, in radio astronomy, OH is the cleanest fingerprint for active water chemistry. Detecting it in absorption rather than emission means there is a cloud of OH gas blocking the background radio signal, soaking up photons at those exact frequencies. The depth and shape of the lines, together with the known geometry, let researchers calculate how much OH is present and by extension how much water is being released. Thermal models, cross-checked with ultraviolet and infrared data, point to a near-surface temperature on 3I Atlas of 230 Kelvin, roughly minus 43 degrees Celsius. At that temperature, water ice does not just sit inert. It sublimates, turning directly from solid to vapor. The measured column density of OH, combined with the expansion velocity inferred from the line width, translates to a water production rate near 1 × 10 to the 27th molecules per second. That is a torrent of vapor, comparable to some of the more active comets ever tracked near the Sun. The timing of the detection was no accident. Attempts in September, when the comet was farther from the Sun, found nothing. Only as 3I Atlas approached perihelion did the heating cross a threshold, triggering the sudden release of water and in turn the burst of OH. The narrowness and stability of the lines rule out local interference and fit the profile of a real, expanding coma. The Doppler shift nudged the signal away from the worst of the solar radio background, opening a brief window where the chemistry could be seen directly. By tracing the photodissociation chain, water to OH, OH to hydrogen, astronomers could for the first time follow the chemistry of an interstellar visitor in real time. The spectrum became a direct probe of the comet's activity, not just a snapshot, but a physical record of how sunlight, ice, and cosmic time interact on a body from another star. 9 degrees on the sky. That is the angular distance separating 3I Atlas from the coordinates of the legendary WOW signal of 1977 at the moment of radio detection, a sliver in astronomical terms, especially given the vastness of the sky. The coincidence is striking, and it did not go unnoticed. Within hours, social media and science forums lit up with speculation, some drawing lines between the new hydroxyl absorption and that decades-old burst of unexplained radio energy from the direction of Sagittarius. Yet for researchers trained in the discipline of evidence, proximity is not proof. The 3I Atlas signal is chemistry in action. Hydroxyl molecules absorbing at 1665 and 1667 MHz, the unmistakable signature of water being broken apart by sunlight. The WOW signal, by contrast, was a single unmodulated radio pulse, never repeated, its origin still debated. The only real connection is geometry, and even that is a product of orbital chance. As one comet dynamicist put it, spatial oddities catch headlines, but the real story is in the chemistry, not the coordinates. Still, echoes of the past linger. Surviving members of the original WOW team, including Jerry Amon, offered measured words to the press, recalling the lessons of 1977. Back then, excitement outpaced caution, and speculation ran wild before the data could be fully vetted. This time, the mood is different. The MeerKAT team, along with technosignature researchers, stressed the need for rigorous cross-checks and a sober reading of the evidence. The hydroxyl lines are narrow, stable, and precisely Doppler shifted to match the motion of 3I Atlas, not the erratic drifting patterns of artificial beacons or the fleeting spikes of terrestrial interference. Public fascination with the WOW field is understandable. The human mind seeks patterns, especially when cosmic coincidences evoke old mysteries. But in the world of radio astronomy, intrigue alone is not enough. The angular separation, about 9 degrees, serves as a reminder. Sometimes the universe offers up compelling alignments that demand both curiosity and caution. Chemistry, not geometry, carries the weight of proof. 8 distinct behaviors set 3I Atlas apart from every comet on record. The first clue comes from its tail. Not only does the tail sweep away from the Sun, but a mirror image anti-tail stretches in the opposite direction. This rare symmetry hints at complex dust and grain dynamics, likely shaped by the comet's unique journey through interstellar space. High-resolution imaging from Hubble and JWST reveals the tail is not static. It oscillates, twisting in rhythm with the nucleus's rotation. Periodic shifts in the tail's angle, mapped over days, point to a tumbling, spinning core whose changing orientation alters the direction of ejected material. Brightness is another puzzle. Over a single week, the comet's apparent magnitude swings by half a point, a dramatic shift for an object so far from Earth. These brightness surges do not follow a simple pattern. Instead, they rise and fall in step with bursts of volatile release, sometimes triggered by jets erupting from beneath the crust, sometimes by sudden exposure of icy patches as the nucleus rotates. Off-axis jets, captured in both infrared and optical bands, shoot material at angles far from the main tail. This suggests pockets of gas trapped below the surface, venting unpredictably as the sun's heat penetrates deeper layers. Trajectory analysis adds another layer of intrigue. The comet's path shows subtle repeated deviations from pure gravity, tiny non-gravitational tugs that can only be explained by uneven outgassing. Each thrust, though minuscule, nudges the orbit. This behavior has been seen in some solar system comets, but it is more pronounced here. Meanwhile, the coma and tail display asymmetries and granular substructure, sometimes resembling fragmentation or the ejection of larger clumps, as if the nucleus is shedding material in fits and starts. Spectroscopy deepens the mystery. JWST and VLT data reveal a composition richer in carbon dioxide and cyanide than typical comets, with traces of atomic nickel vapor, unexpected for an object formed far from our Sun. The surface itself tells a story of endurance, a refractory crust, baked and altered by billions of years of interstellar radiation now exposed to solar heat for the first time. Each anomaly on its own might be explained by known cometary physics. Together, they form a catalogue of strangeness that demands forensic scrutiny. The case for 3I Atlas as a natural comet is strong, but the evidence compels a deeper investigation into how such an object could emerge from another star and arrive so active in our own. Discovery of 3I Atlas came just after midnight. UTC on July 1, 2025, flagged by the Atlas Survey Telescope in Chile during a routine scan for near-Earth objects. The initial orbit was unmistakable, a hyperbolic trajectory inbound at 42 kilometers per second, far too fast for any solar system origin. Confirmation followed within 24 hours, as 31 observatories submitted their own astrometry, and the Minor Planet Center assigned its designation 3I, the third interstellar object ever recorded. Perihelion arrived on October 29, 2025, at a distance of just 0.66 astronomical units from the Sun, inside the orbit of Venus. At that point, 3I Atlas was racing through the inner solar system at a speed that left even seasoned comet trackers scrambling to keep up. Its path, geometry, and velocity set it apart from the familiar parade of periodic comets. This was a true interstellar interloper on a one-way journey past the Sun. Placed in context, 3I Atlas completes a trilogy of cosmic visitors. The first, 1I Oumuamua, stunned astronomers in 2017 with its peculiar acceleration and lack of any visible coma, a dry, tumbling shard that defied easy classification. 2 years later, 2I Borisov entered the scene as the archetype of a comet, trailing a textbook coma and jetting cyanide, water, and dust in patterns familiar from solar system cousins. Now, 3I Atlas brings a new profile: active, volatile-rich, and, for the first time, a source of direct radiochemistry. The orbital parameters tell their own story. All three objects followed hyperbolic paths, but only Atlas was discovered early enough to allow pre-perihelion planning for a coordinated global campaign. Its inbound speed, combined with a close approach to the Sun, created a rare window for observing volatile release and chemical processes in real time. The challenge was not just detection, but rapid validation. Every minute between discovery and perihelion mattered, as the object brightened, outgassed, and then faded back into the void. For comet dynamicists, these three interstellar visitors form a comparative grid. Oumuamua, odd acceleration, no coma, no chemistry. Borisov, classic comet, standard chemistry. Atlas, active, anomalous, and, crucially, radio-confirmed water chemistry. Each arrival rewrites the expectations for what lies beyond the solar system and raises the bar for forensic scrutiny. The stakes are not just academic. With every new interstellar detection, the pressure mounts to build a playbook that can catch, characterize, and cross-examine these travelers before they slip away forever. Confirmation began with a forensic audit of every step from detection to alert. The MeerKAT team preserved raw visibilities, calibration tables, and the full log of automated and manual flags. Two independent analysis teams using separate reduction pipelines reproduced the spectrum from scratch, matching line frequencies, widths, and Doppler shifts within measurement error. Each group applied distinct bandpass calibrations and baseline fits, ruling out software artifacts or operator bias. Solar radio contamination was modeled in detail, simulating the 3.76 degrees separation and injecting scaled solar flux to test for spurious absorption. No combination of side lobe pickup or background fluctuation could mimic the observed doublet, especially at the precise velocity offset of -5.6 kilometers per second. External follow-up requests went out within minutes. The Green Bank Telescope, FAST, and VLA all received the alert, but geometry and sun avoidance protocols limited immediate response. As of mid-November, no public reports from these arrays have confirmed or refuted the signal, leaving MeerKAT's detection as the sole direct evidence. Meanwhile, ultraviolet and optical campaigns tracked outgassing patterns and brightness surges that matched the expected chemistry, providing indirect support. Every log, spectrum, and calibration file remains archived for outside review, anchoring the discovery in a chain of evidence that stands up to the highest standards of radio astronomy. Precision. In radio astronomy isn't just about distant comets or rare cosmic visitors. It's the same discipline that allows astronomers to track Earth's shifting neighborhood. In August 2025, a new quasi-satellite, 2025 PN7, was identified looping near our planet, its orbit tangled in Earth's gravity for just a few years before drifting away. This kind of discovery shows how the boundaries of near-Earth space are constantly redrawn, with objects slipping in and out of our neighborhood almost unnoticed. On a larger scale, the same attention to detail powers the search for gravitational waves across the galaxy. Pulsar timing arrays, spread across continents, monitor the ticking of millisecond pulsars to catch ripples in space-time itself, subtle signals that would vanish without decades of precise, coordinated measurements. On yet another scale, the James Webb Space Telescope maps the atmospheres of ultra-hot Jupiters orbiting other stars using the same spectral fingerprinting that flagged hydroxyl in 3I Atlas. Whether the target is a near-Earth companion, a galaxy heartbeat, or a distant exoplanet, the methods unite them: chemistry, timing, and the relentless push for clarity. Each breakthrough, no matter the scale, sets the stage for the next generation of surveys designed to catch fleeting cosmic phenomena before they disappear. Rubin Observatory's legacy. Survey of space and time is about to change the game for interstellar discovery. Its wide, deep sky coverage and rapid alert system mean that new objects, especially fast-moving, hyperbolic visitors like 3I Atlas, will be flagged within minutes of detection. The cadence is relentless. Every patch of sky gets revisited every 3 to 4 nights, with specialized programs able to push the frequency even higher for areas of interest. But discovery is only the first step. Rapid follow-up, optical, infrared, and crucially radio, depends on a global relay of telescopes ready to pounce the moment an alert drops. ESO4. Most spectrograph brings a different kind of muscle. Hundreds of targets can be sampled in a single sweep, each spectrum revealing the chemistry and velocity of distant objects. But fast-moving targets demand nimble scheduling, and operational delays can mean missing a fleeting perihelion window. The next-gen playbook calls for dedicated protocols, reserve blocks for emergencies, simulation-driven drills, and a standing network of observers, professional and citizen alike, primed to respond. The challenge is clear. Catching the next interstellar visitor means acting faster, coordinating better, and thinking beyond the usual survey routines. With Rubin and 4. Most leading the charge, and the world's astronomers and citizen scientists on alert, the hunt for cosmic travelers is entering a new era. The invitation is open. The next signal could appear at any moment, and anyone could help write the next chapter. Today, we listen for chemistry, not just messages from the stars, and every new detection sharpens the search. As observatories like Rubin scan deeper and faster, interstellar visitors become laboratories for questions about water, origins, and intent. The cosmos leaves fingerprints in chemistry, not code. What we find next may challenge where science ends and speculation begins.